Hello, this is Tyler Linder, and this is my third lab report for Physics 2211 for fall 2020, and the title for this lab is the black hole. First up, we have the introduction. Again, the topic of this lab is the black hole, and the procedure for this is to edit a GlowScript starter code. In the code, we must generate a unique star trajectory keyed to our email addresses. After that, we analyze the star's orbit, we find the assigned net forces, and then we find the black hole's mass. The assigned net forces include perpendicular and parallel net forces. The fundamental physical properties of this lab include momentum principle, Newton's law of gravitation, Newton's second law, and parallel and perpendicular forces. For the system properties and initial conditions, we had to include most of these values into the code in order to generate the motion of the star. First, we have the gravitational constant, then we have the mass of the star. After that, we needed to incorporate the black hole's position, and then also the time interval between data points, which is 1 day in seconds. After that, we use the fundamental properties to find the x and y component of velocity. Moving forward, we must calculate the net force of the star. To do so, we must define the initial and final velocities, and then compute the initial and final momentum vectors. Once that is done, we must find the change in velocity and momentum of the star. After that, we find the net force using Newton's second law, and then using delta t, initial and final momentum vectors, we must find the parallel net force. Once the parallel net force is done, we can also find the perpendicular net force. After calculating the net forces, we must calculate the mass of the black hole. In order to do so, we must first find the position of the star. The position of the star is equal to the vector of the x-index, the y-index, and nothing for the z-index. After doing so, we must find r. The r value is equal to the magnitude of the position of the ball subtracted from the position of the star squared. Once that is done, the mass of the black hole can be calculated. That is equal to the magnitude of the net force times the r value, all divided by the gravitational constant times the mass of the star. Here is a video model of the star orbiting around the black hole. The 3 arrows represent the net forces acting on the star. Once the code has been complete and ran, we get the mass of the black hole, the net force, the parallel net force, and the perpendicular net forces all printed out. The mass of the black hole, as you can see, is 1.43931 times 10 to the power of 34 kilograms. The net force is 8.95463 times 10 to the 28th power. The parallel net force is 1.5426 times 10 to the 28th power. The perpendicular net force is 8.82903 times 10 to the 28th power. So what does all of this mean? We can answer how the net force and its parallel and perpendicular components are different from the rate of change of momentum in its parallel and perpendicular components. We know that the net force creates a change in momentum. The parallel net force affects the speed of the star's orbit. The perpendicular net force affects the direction. These forces are similar in direction, however, they are completely different. They're different in that the calculation procedure are all unique to each other. So what if the black hole was replaced and everything else stayed the same? It is possible that you can tell a difference if this occurred. The star's motion would change because of the gravitational force would change. Also, you can find a new mass of the black hole.